So yes, we're going to talk to you about networks, give you the basics. Hopefully you guys kind of have a basic understanding of how networks work so you guys can kind of get started on your own on learning more about network security. So first off, what is a network? A network is basically just, it's like a connection between computers. So it's like a system of interconnected computers. If you guys went to Peter's What Shape is the Internet talk, you guys remember this slide. When Peter did his talk, he talked about how the internet is connections between people. But if we kind of take that closer look, we can also see that those people are connected because of networks and their computers. So when you have the internet, so the internet is actually just like a network of networks. So when you connect on your computer, you're connecting to a network, and then that connects to another network, and yes, it just keeps going.
Okay, so when I look at what actually using a network looks like on the perspective of a single computer, one computer has its connection, and it's connected to another computer, and it sort of goes through a bunch of layers of like concepts that are important. So the bottom layer is the physical layer, right? It's obvious, that's a cable. Getting there more, and then there are a bunch of other layers that do a bunch of things. Up to the application layer, which is like a web browser, right? So there's everything in between, and that's the OSI layer. So the internet runs on TCPIP. The OSI model is an older model of how networks are supposed to look. It was based around phone systems, which are not how the internet works, unless you're on dial-up, and then the OSI model might be more relevant to you. But in TCP/IP, the physical layer and the data link layer, which I'll get to in a minute, are a lot more closely bonded. And it's sort of, there is a distinction there still, but the data link layer really heavily depends on how the physical layer behaves. It's not like a phone where you can just put a wire in between two things and it's like, yeah. And then like next up we have the network layer, the transport layer, the application layer, and we'll be getting to those too. So physical layer first, pretty clear. Ethernet cables, routers, and you connect to Wi-Fi. There's probably a router in this room or very near to this room since I do have internet right now. Oh look, some physical layer components. So the data link layer builds right on top of the physical layer. And the data link layer isolates things in terms of packets. So a packet is like one little chunk of data that gets sent over some network element, either a wire or a wireless signal. And each of those packets is individually addressed to go to a different location. So the data link layer uses what's called a MAC address, which stands for that thing, which I did not know before I looked it up, and it's not important, it's a MAC address. So a MAC address looks like this. It's 6 bytes that are usually written in hexadecimal, separated by semicolons, separated by colons. Promise I didn't fail English. Well, only once. So the MAC address is programmed directly onto the NIC. That's the network interface card. So your actual physical piece of hardware has a MAC address that was printed onto it in the silicon at the manufacturer, and that's what it is. So that address is used for communicating on a local network. So that's only computers that you're like immediately connected to. So if you're all on the same router, for example, so like, oh, let's connect to that one right now. So we can all talk directly between our MAC addresses. And that's how the traffic that goes between us will work out. And when we go outside of the network, hit it. So that's this layer. This is just getting data around the local network. And so those things on the local network, those entities, can be computers, or they can be routers or other network hardware. They all use the basic network access layer to talk to each other. Yeah.
So yeah, but first we're going to jump now to the next layer up, the network layer on the OSI side, internet layer. And so the network layer is, so kind of going next step is how your data is going to be sent out to the other networks. So this is used by adding an address to your packets that are being sent. And this is also going outside of the local network, to be clear. So you have like your local network that's kind of interacting like with your router, and then you go out and you're going into the wide area network. And so what it does is it uses your IP address, which is your unique identifier. So kind of using the whole like post office envelope metaphor. So if you put your letter into an envelope, this envelope is going, the IP address is like your home address. It's a unique identifier so they know how to send the data to your house. So IPv4 and IPv6 are the different IP or internet protocols. IPv4 comes before v6, and it's made up of 4 bytes. And the reason they actually are starting to use IPv6 is because we are starting to get through all 4 bytes, and we've used all of the IP addresses, or we're close to it. So now we have IPv6, which is 16 bytes, and thus we are not yet using that one up. Yeah.
Okay, so one of the ways that we're addressing the lack of new IPv4 addresses is something called network address translation. This is also how every home router works. So a router that is managing your local network will broker your connection to the internet for you. So when you say, I want to connect to Facebook, you send that data over the local network, your router picks it up, it connects to Facebook for you using its IP address, and then gets that data back and gives it back to you to your local IP address. So when you're on a local network, there are reserved subnets in the IPv4 space that you can't use for the open internet. You can only use to represent subnets. A lot of you probably recognize this one, 192.168. So that is used for a reason, and that's because it's reserved for local networks. So that's why they usually have that address on your router. The other big one that's used is the 10. etc. You can use that entire major address space for a local network, which contains over 16 million addresses possible, so it's a little big. But people use it, mostly organizations. White Hat also uses it in the lab. We're a 10. Address space. So the nice thing about this is there are probably a lot more than 4 bytes of computers. That's like what, 4 million, 4 billion? Some large number. Pretty sure it's 4 billion-ish. And there are a lot more IP addresses that have been allocated to that. And that's because a lot of them are going through network address translation. So if you have 5 computers at home, you're only using up 1 IP address on the open internet because that's your router, and everyone else is behind the router on a 192.168 address.
So now we are going to move on to the 4th layer, the transport layer, as used the 4th in the OSI model. And so the transport layer determines how your packets will be routed internally. So now we've talked about all of these packets, this data getting transferred. Now it's reached your computer, and the data is on so the traffic is going towards your computer, and now it needs to figure out, your operating system needs to figure out where it's going to go, which programs are going to get that data. So to do that, here's kind of a diagram displaying how that works. So this level is what assigns your port number and then the protocol that's being used. So here's kind of a good example. So you have all of this data coming from the internet, so it's reached your computer, and now it's going to determine based on the port number which program it goes to. So each program will run on its own and listen on its own port. So for example, web server will be on port 80, and then so SMTP 25, whenever you guys SSH onto the Unix servers, that's on port 22. And so that's how it knows where to send that data, and then go back.
TCP.
Yeah. Oh, yeah, I think I went. Yeah, I made another slide. Okay. So then also it assigns a protocol. So if it chooses if it's going to be sent through TCP or UDP, and now we'll talk a little bit specifics about those.
So TCP stands for Transmission Control Protocol. I'm pretty sure everyone calls it TCP. TCP is like a bidirectional stream-oriented protocol. What I mean by that is you connect to someone, you send data to them, and they reply to you. It's like a conversation.
Like a handshake is what they call it.
Yeah, so there's initially a handshake in TCP where you say hi, da, 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 and then you have a connection, and you go from there. So that connection has state. Mostly it guarantees that the packets that you send will arrive in order. So if it gets one that's later on in the stream. So for example, in a Netflix video, if you get like the second after the one that you're supposed to display next, then it'll wait for the original one to come in, give that to the program, then send the one that got there early. So, and it also takes care of packet loss and like intermittent network failure. So if you are downloading a file or whatever, and one of the packets gets dropped, it's not going to disappear from your file and be gone. TCP will take care of like saying like, oh, I didn't get this part, okay, I'll resend it, woo, great. So this is mostly used for file transfer type things, or like video streaming that's non-real time, like Netflix. If you want to have like, if data integrity is really important to you as opposed to like really low latency, because if you want to ensure that like you'll get every single bit of data, literally every bit, then TCP will TCP will ensure that you get that, even if it means waiting and like not receiving any new data until the stuff you need comes along.
And then, so now UDP in contrast is connectionless, and there's no state as well. So instead of having this handshake where you have like this back and forth dialogue kind of thing happening, it's much more one way. So you're just kind of like setting data at the server or wherever you're sending it. So this is more important if you're wanting a fast connection and you don't necessarily care if a couple packets get dropped because there isn't any error checking, or well, there isn't really a lot of error checking. So this is used video streaming, so if you're Skyping or FaceTiming, whatever, online games, voice over IP, DNS or DHCP. So that's kind of like if you're broadcasting over the network and you're just telling everybody like, what's my IP, and so you're trying to get that really quickly, and then someone will just respond back. So you don't necessarily like need this whole connection being maintained.
Yeah, DHCP in particular, like DHCP is Dynamic Host Configuration Protocol. And so basically what that is when you connect to a new network and you don't have an IP address yet, then you can send a UDP packet. And it says like the source. It's like sending a letter with no return address. It's just like help. Some administrator of this network configure my IP address, and then DHCP server will give you a DHCP lease, and then you have an IP address, and then you use that going forward.
Yeah, it's commonly used like with live things too. So you know, if you don't really care, like if something gets missed, you don't want it to like stop and then go back and like, okay, what was that packet I missed? Things like that. You just like want it to keep going. So this is summarize that.
Yeah, so that's basically all the layers that are important. These other layers in the MSI model sometimes apply, but they're really like a bad metaphor for TCPIP. So to review, we talk over the network to other entities on our same network that we are directly connected to. Some of those entities, like routers, are capable of brokering our access to the open internet. And then the computers have meaningful protocols they talk to each other with, like TCP or UDP, that they talk to each other with. And then applications like web browsers, web servers, email clients, email servers, many other client-server pairs will use network protocols to talk to each other and do good things. Yeah.
So now, how to attack networks. So, so one of the first things that you're going to do, hypothetically, not actually, but if you're to attack a network, is generally the attacker would do some kind of reconnaissance, learn what programs are being run, and so say if you have an exploit that you found or have found yourself or from somebody else, and you have an exploit, you maybe want to look for the program that you use that exploit on. So this kind of goes back to this diagram a little bit. So for ports, what you can do is you can kind of send a like TCP, or you can send a packet to the ports. And so what that does is like scans all of the ports. Like this is just on one system. So you can scan all of the ports on one system, and then you'll get that response packet back if it's a TCP connection saying, and so from that you can learn about what programs are being run on that port or are listening on that port. So, for example, you can learn like the version of the program, you can learn if it's like an older version and maybe there hasn't been a patch been done on that version yet, or you can learn about the operating system that they're using. So it's a great way to learn about what kind of attack vectors you have on a system.
That's called fingerprinting. We can't objectively learn what operating system something is, but if like Windows XP usually has like these certain services open on these certain ports, and they usually say things like this, then certain tools will check that, detect that, and they'll be like, oh look, this looks really similar. This is probably a Windows XP machine. And it'll give you that fingerprint.
I forgot to mention, one way of doing that, we'll bring it up again at the end, is using a tool called Nmap, and that's one you can use for port scanning. Oh yeah, so then there's kind of like those two types of scans, and there's TCP scan and SIM scan. So similarly, like what I said, the whole handshake thing, so you send a packet and then you receive that response back. And then what you'll do is like you can just kind of like cut the connection, and so like end the handshake after that full handshake has been completed. Or the SIM scan is you're just sending the initial like hello, I'm here packet, and then you don't really care, you just like get the response, and that you just kind of like learn just from that, and so you don't like complete the whole connection.
Quickly about port scanning. If you port scan the security lab's IP address, it will say there's no computer there.
And don't port scan on the Cal Poly network, because you can get in trouble for that.
That's against the responsible use
Yes.
policy. So, regarding the internet as a series of tubes, this is actually the full context of what he said, and this is actually true. Like, you can fill up the tubes, and that's called a denial of service attack. He was talking about net neutrality, Netflix filling up the tubes with all of their videos, but, you know, screw him. So the big issue with denial of service is if you're pumping a ton of shit into the tubes, then the other messages that are trying to also go on the network are not going to get through as quickly, or maybe not at all. So if like a reasonable amount of stuff to go to a web service is like 10 users, and then all of a sudden you shit on like 10,000 connections, all pumping a ton of data, opening and closing connections really fast, those 10 users are going to have a very low probability of getting service. So that's called a denial of service. Ah, yes. So a common way this is done is with botnets. And so if a hacker collects a large number of computers by infecting them with viruses and controls them as part of his botnet, he can command each of the individual zombie computers to all request something from some server that he's trying to DOS, and presumably that would be, you know, you have a lot more zombies in this botnet than the normal users of the site. So if this industrious hacker attempts to DOS Google, probably not going to get anywhere since they're already prepared to handle that many searches per second. But if they're trying to DOS like mom and pop's donut shop San Francisco, probably mom and pop's donut shop is totally
So then another way of doing that is something called IP spoofing. So what you can do is when you send a packet, you have like the to IP address and the from IP address. And so what that means, like that from address tells the computer you're sending it to like where they need to send their packets back. So what you can do is you can send a packet with a fake, or say if you want to attack a specific IP, you can put that as the from IP address. And so then if you send a ton of packets to a bunch of different computers with that fake or with that like target IP address, then it will send all of their responses to that target server, and then also that's how you can DOS them as well. And then, so this is for session hijacking. So another way, one thing is IPs aren't always authenticated. So one way you can kind of pretend to be someone else is also with IP spoofing. So say you have an authenticated user that is connecting to a server and you also want to connect to that server, but you aren't authenticated, you can use their IP, or as long as like some other things work out. But you can use that IP and then pretend to be that person and kind of like hijack their session. So one issue, I don't know if you guys use WhatsApp, their traffic, they send their packets unencrypted. So something you can also do with that, you can see their traffic, and there's a lot of known vulnerabilities that have been found with WhatsApp.
So what's awesome about that is you can actually see their traffic, spoof the IP address of the person who's talking, and then inject stuff into the conversation. Because it's not encrypted, so you can do anything to it with IP spoofing and hacking it. So one of the big ways, Brian, we didn't change the slide. So one of the biggest attacks that's ever been done on the public internet was an NTP reflection attack. And so that was kind of what Cristina was talking about earlier about using IP spoofing to attack somebody. So the way this attack specifically works is there's a vulnerability in NTP software, which is network time protocol. And basically there are a bunch of time servers all over the internet that keep very accurate time. And you can ask them what time it is and they'll tell you. And your computer does this periodically to make sure the clock stays correct. And this protocol, there's one server that's really popular for NTP servers. And so they added an extension that allowed you, I think it was an extension, tell me if I'm wrong.
Just NTP, it's the protocol.
Oh, just in the regular protocol itself. NTP, you can ask for like the last n number of requests serviced, which is an entirely pointless feature that should probably only be used for debugging. But what these hackers realized they could do is they could spoof the IP address of someone they were trying to attack, like Cristina was talking about. And they could say like, all right, send me as many entries as you can about what's the request supply service, but then they are asking for that from a different source address of the server they want to attack. So this server is like, okay, let me look at all the things I just serviced, and then it sends it back to a different machine than who sent it. And so if you get a bunch of machines sending these spoofed packets to a bunch of servers, those servers are then going to send a ton more data back to the target server. So that's why it's called a reflection attack, because you're sending like a malicious packet to one server, and that attack is being reflected off onto the actual target. And in this case, this is also an amplification attack, because the amount of data you have to send to the NTP server to get it to send back that huge list is like really small, relatively speaking. It's like 1/50th or something.
250th.
1/250th. So if you have like n gigabytes of bandwidth to execute this attack with, if you reflect it off of NTP servers, you can do 250 n amounts of data sent to the target server. So you need a lot less bandwidth to execute the attack. And the attack actually, when it was executed on the public internet, was something like, what, 300 gigabytes per second?
It was ridiculous.
Really big.
It slowed down all of Europe's internet.
Yeah. Good.
So, finish up, we wanted to give you guys some things you guys could look into after the talk. Like I mentioned before, Nmap is a good port scanning tool if you wanted to start learning how to use that and learn how to port scan. Again, don't do it in your dorms on the Cal Poly network. Wireshark is another good one to look into. It's a packet sniffer. So you kind of set it up on your computer. You can view all like incoming traffic coming through your computer. And you can analyze, so you can see like if it's TCP versus UDP, IP addresses, and like different information about it. And then
and then IP tables is the firewall sort of software on Linux, except it's a lot more than that. It has a sophisticated rule chain system that allows you to do whatever you want. So you can actually take arbitrary packets and rewrite them to anything else. So you can transform network traffic in ways that can be fun or malicious. One of the things I like to do with this is I have this demo where whenever you go to a website, I smash your packets and handle the request myself. And then if you request an image, it turns it upside down and then sends it back to you. So that's one of many fun things you can do with IP tables. But do note that with the exception of running a firewall on your computer, all of these things are not allowed on campus, so you have to come to the security lab to do them. Or the networks lab. The networks lab also, but I think you can only get in there if you're actually taking CS 464. Yeah. But 464 is a great class. It's my favorite class. Everyone should take it. Andy's taking it. Pretty amazing. Bomb.com.
that is it. Yeah, that's it. Does anyone have any questions? Yes.
You're just like passively using Wireshark, isn't that like, that's detectable?
Yes.
Yeah.
So,
Still against policy though.
yeah, well, A, it's against policies with over-the-shoulder problem. Like the current privacy mode, people does not protect you from over-the-shoulder attacks. But yes, because if your Wireshark, in order to work, sets your NIC into what's called promiscuous mode, which means normally your NIC filters out things that aren't destined for its MAC address. And since the MAC address is programmed in the NIC, it can do that really quickly, which is why it does that. Network interface card, I already said you weren't here. Get out! But if you set it to promiscuous mode, it won't do that, and it'll just take everything that it gets off of the network and give it to your operating system so that Wireshark can read it. But the problem with that is there are a lot of things that get sent to the network that you shouldn't necessarily be able to see, that you don't need to see, which would get filtered out by your network card, but some services on your computer will respond to. So it's non-trivial to detect the use of Wireshark, but you can. And I doubt that campus IT does that, but you still shouldn't shark people's networks without permission. That's super poor form. I mean,
There's no real benefit other than getting information that you shouldn't have from those people.
Yeah, it's pretty unscrupulous. What up?
Is it against network use to spoof your MAC address?
Yes.
Is it?
Yes.
Isn't there some sort of protection against connecting to the network with a spoofed MAC address? Like, isn't your MAC address associated with your account?
So, cheaper NICs can't actually change their source MAC address, but most of the modern NICs that are in any computer since like the mid-2000s will be able to write arbitrary packets to the network. So you will be able to spoof your MAC address. It's just, like, again, there's no reason to do that besides questionable activity. So don't do it on the public network. What up?
How do you, like, if you were going to set up a web server to go live on the internet, how would you get assigned an IP address for that server to use?
So,
Or a router for that?
yeah, you basically ask for it. So an ISP can sell you an IP address on their network, a public network, and that would be the way you would do it if you like literally wanted to set up your own hardware that was yours in your house that had an IP address for a web server. But the real way to do that in the real world is use the cloud and get something on like EC2, Compute Engine, or any number of web hosting sites like DreamHost, GoDaddy, Heroku is really good for that. DigitalOcean, like I could list these all day. There's so many companies that will give you space on the cloud to put your stuff. So
With a dedicated IP address.
yeah, with a dedicated IP address.
And with the GitHub student developer pack, you can get.
Yeah, $100 of DigitalOcean.
20 months
free.
of DigitalOcean.
Yeah. 20 months. Yeah, DigitalOcean VPS is a virtual private server. Is $5 a month, and if you get the GitHub student developer pack, it gives you $100 of DigitalOcean credit, so 20 months.
And .NE domains.
And .NE domains. Really?
For a year.
You get a single
You get a .NE domain.
I'm doing
Just
that.
one.
You're fine with .NE?
It's only for a year too.
I'll renew it after that. It'll be great. That's saving like $40. Me domains are expensive.